at our website.
Sorry, Bill, continue.
We have a membership forum on our club website at www.chiastro.org, maintained by our webmaster, Jim Guilford. Hopefully, we will be able to get back to regular in-person meetings at Rocky River Nature Center sometime in the future. However, for the time being, our meetings have been canceled by the Metro Parks through August. No word yet on September, October, November, but hopefully we'll be able to get back to in-person meetings. Tim Campbell, our Vice President, is in charge of our speakers program, and Tim has arranged for our speaker, Professor Monreal, to join us tonight via Zoom. Tim, would you like to make the introduction?
Sure, thanks, Bill. And I'd also like to add my thanks to everybody for coming out tonight. This is the first club meeting at which we do not have to wear pants. So our speaker tonight is Benjamin Monreal. Ben is the professor of physics and astronomy at Case Western Reserve. His specialty is experimental particle astrophysics. He deals in neutrinos, dark matter, and the intersection of nuclear particle physics with stellar galactic astronomy. So it's pretty hardcore. Tonight he's going to talk about telescopes, which is good because we are a telescope club. But he's talking about telescopes that are a little bit larger than Paul Leopold's. There are 5 10-meter telescopes in the world today, and there are 3 30-meter scopes in some level of construction. And so what he's going to talk about is the engineering and imaging in these largest telescopes that makes them possible. So without any further ado, I give you Dr. Ben Monreal from Case Western.
All right, thanks very much, Tim. I appreciate the invitation. I'm sorry you couldn't be there in person, but it's the times. So again, there's a chat window in your Zoom menu, and I'll see those chat. If you type something in there, I'll see it right away. I might not respond to everything that comes up in the course of the talk, but if there's something you just need me to repeat or something, just type that at me and I'll try to get to it. Let me start this display and I'll try to share my screen. So I think you will all see this, but we'll do a quick check to make sure that's the case. Screen. I want to share this one.
That's good.
Okay. Need to hit. There we go. Okay, so you can all see my screen. You can all see. Can you see my cursor, my actual mouse? Because I'll be using that to interpretive dance at you while we're doing this.
That's good.
Cool. So we'll go ahead and get started. So I'm a professor in the physics department at Case Western. I was not. My prior experience has always been in places where there's no physics and astro departments that are separate. I've always been in. Before coming to Case, I was always in places that had a single physics and astronomy department. Case has the 2 separate ones, and I happen to be on the physics side, which is where most of my training is. But truth be told, I was trained in nuclear and particle physics, and I was always at places where the nuclear and particle physicists were either out of town all the time because they were off at an accelerator somewhere, and some of them were just really boring people. So I spent most of my career hanging out with the astronomers. So I have a lot of background on the astro side without having taken all that many classes in it. Especially in my last appointment at UC Santa Barbara, there were a bunch of people working on exoplanets, and I quickly learned that exoplanets are interesting. While there's a community of people who are trying to build giant space telescopes to see them from orbit, which maybe will be the place we learn the most about them, it is increasingly, people think that we'll learn a lot about them from the next generation of ground-based telescopes, so I'll talk a bit about that. However, the other thing that probably know, and that if there was something, there was a big New York Times article about it a few weeks ago. These giant telescopes are really expensive, maybe too expensive. Maybe they're more expensive than society wants to spend on 30-meter telescopes. So I have one of my side projects, and the thing I want to talk about today is an idea that I've had and I've been working on to try to observe exoplanets from the ground for much cheaper than the TMT scale that everybody else is doing. So yeah, so let me get this. So I know you're all people interested in astronomy, so maybe I'll be telling you a bunch of optics that you already know. I'll try to go through it quickly. So just to get the scale of exoplanet observations compared to the scale of small telescopes. One nice place you can get professional all-sky data is from the Sloan Digital Sky Survey. They have this, you know, it's mostly an unremarkable telescope, but with a very nice camera on the 250 centimeter Sloan instrument. And so this is the Sloan image of a star called HR 8799. That's something which is known to have planets orbiting around it. And we'll see the planets in a minute, but we're not going to see them from Sloan. So I'm going to zoom in on this image. This is the best they have in their 2-meter telescope. You can see here's the field. This is, I believe, an unrelated field star. And as you zoom in, what you see is, well, there's actually a bunch of features of this image which are relevant to the exoplanets. One is this bright spot in the middle. That is the central diffraction spot. And this is the size of the diffraction pattern you associate with a 2.5 meter circle at invisible wavelengths. So this is just light from the star, which is spread out over the detector. And if there was a planet also illuminating the detector, you would never see it if it was in here. These things some of them are diffraction spikes associated with starlight diffracting through the aperture, which has other little features in it. Some of them are CCD artifacts, just the presence of lots of light from this star on one strip of a detector can lead to some readout artifacts, some of which have been subtracted, but not perfectly. That's the kind of thing that happens. So I'm going to keep zooming in, and let's see, zooming in further. This is as far as we're going to go. If we let the diffraction spot fill the entire screen, we are still not at the scale where you would be able to see solar system type planets. If Earth and the sun were resolved in this image, they'd be a few pixels apart. They'd be really close together. Even out to Uranus, Neptune, Pluto, that's all stuff that just disappears into the diffraction spot of a 2.5 meter telescope. So any hope of, and this is HR 8799, we'll see what the planets look like in a second. There's no hope for resolving planets like this with small telescopes. We have to go to big ones. Let's go to the biggest. So here's same system, same plate scale on your screen for the 10-meter Keck observatory, or one of the Keck telescopes. This is probably composite from both telescopes. So this is a heavily processed image taken over many years. So remember, with the 2.5 meter telescope, the diffraction spot filled this whole box. Making the telescope 4 times bigger means the diffraction spot is 4 times smaller. So the starlight is concentrated in this little dot in the middle, giving you some nice dark sky. Not perfectly dark sky, but a nice clean CCD without too much light on it. The starlight has been elaborately subtracted from this image, and there are these 4 dots of light, which are not the star. And in a few years of observations, they were seen to be going around. So these are the 4 of the giant luminous Jupiter-like planets of HR 8799. Again, this is nothing like the solar system. For one thing, the light you're seeing in this image is not the starlight reflected off the planet. What you're seeing is the planets glowing with their own heat. Whether it's a bit of nuclear fusion because they're sort of like big little brown dwarfs, or whether they're recently formed planets and they're still collapsing and they have some heat from their gravitational energy. I'm not sure about that. But yeah, this is not solar system stuff. This is not looking at Saturn and seeing light bouncing off the rings. This is seeing 4 tiny stars. But it gives you a sense of the scale. The 10-meter telescope, we're resolving stuff that's out by Uranus. But if HR 8799 had a Jupiter, you wouldn't see it. It's still in the diffraction spot. Even if it had a Saturn, maybe it's technically outside the main diffraction peak, but it's going to be buried. Something like a dim planet image would just be buried in all the speckle noise, the diffracted starlight, which you can't subtract quite perfectly. And that's on a 10-meter telescope. Cool, but this is beautiful animation. I could watch this all day. Let me move on. So again, back to 2.5-meter telescope. The whole thing is covered in starlight. You can't see anything. So that higher resolution is one of the things that motivates the construction of the next generation of telescopes. So let me just show you 3 pictures of 30-meter telescopes. Here's the giant Magellan telescope. This is the one that I think is furthest along construction-wise. A bunch of these mirrors are cast, and some of them are, I believe, at least one of these mirrors is on the mountain already. The foundation for this whole facility has been poured. And so there's a lot, not all of the money for finishing it has been secured, but they think they're going to finish building it. And that's the GMT. Notice it's basically 7 8-meter telescopes just glued together. This old-fashioned technology. Giant mirrors. The ESO, the Extremely Large Telescope, is being built entirely by Europeans. Again, construction and of most parts is well underway. This has taken more of the Keck-like approach of lots of tiny mirrors tiled together into the main mirror. The second American-led project is the 30-meter telescope, the TMT. Construction is started. Lots of the mirror segments have been secured, but they're not sure if they have a claim to their first choice of site on Mauna Kea, and so they're continuing to evaluate where they're going to actually locate this thing. Again, all 3 of these things have budgets north of $1 billion. TMT is coming in at 1.4 is the current estimate. I think the others are comparable. They're very, very expensive instruments. EELT, this is actually a 39-meter telescope. So this is the biggest, probably closer to $2 billion. I'm going to take a look at this. I'm just going to make sure I can see the chat. So yeah, the two highly segmented telescopes, GMT and ELT, are in Chile. I don't remember which peak. One's neither of them are on a peak with another telescope. Like they're not right next to Subaru or something. They're on some newly developed peaks. TMT may be at Mauna Kea, and it may be at Canary Islands. Those are the 2 main options. So yeah, so let's just review the physics of why these telescopes are able to work and why they're able to deliver high resolution images. Even what does it mean to have a high resolution image? So it helps to think about the wave optics, and always to think about a telescope as being an object, a device that manipulates a big wave. So starlight coming into a telescope is a bunch of plane waves. The star is very far away. It's sending all this electric and magnetic energy at you. But since it's so far off, the light that hits, since I made the image horizontal, I'll talk about it as though it's horizontal. The light that hits the top edge of your telescope, if your telescope is aimed at the star, the light hitting the top edge has traveled exactly the same path as the light hitting the bottom edge, so all the energy arrives at the same time. So you have parallel flat wave fronts coming in. If you wanted to translate that into radio wave terms, you can say, well, there's a flat sheet where the magnetic field is high, followed by a flat sheet where the electric field is high, followed by a flat sheet where the magnetic field is high in the opposite direction. And these flat sheets just march towards you from the star. When they hit the lens, what you want is lots of electromagnetic energy to arrive in one place. You want to pick a part of your detector or your camera or your eye or your film and have all the electromagnetic energy arrive there, not spread out over your whole aperture. So the only way for electromagnetic energy to actually show up somewhere is if, if there are places back here where there's a positive magnetic field, and then there's a place a little bit later where there's a negative magnetic field. If you try to combine the peaks and the troughs of these things, they cancel out and the light cannot arrive in those places. The only way to get light to actually arrive somewhere and light up your detector is to have these flat wave fronts start converging. So the way I like to think about it is, to get light from the top edge of this aperture to the center of the detector is a long path. This diagonal path is kind of long. To get light from the center of the bore to the detector is a short path. So to make light from this path and light from this path arrive at the same time, you have to delay the light in the center. That's why lenses are thick in the center. Light goes slow here, and a lens is shaped to slow the light down just enough so that it arrives at the detector at the same time as light from the corners. You can do the same thing with mirrors in reverse by deciding where the mirror goes. So let's move on. So if you have two sources, their light, you know, if you actually looked at the magnetic field inside the lens, they're hideously complicated because this light and this light are all on top of each other. But the amazing thing about electromagnetism is that all sort of unwinds itself when you get to the focal plane. We can, oh, I can just keep going. So if you have two stars shining in different directions, this is my last one of these, you end up with two spots of light. This spot on your detector is very good at picking up coherent, the energy of parallel wave fronts coming in this direction. This spot in the detector is good at picking up parallel wave fronts coming this direction. So you get two spots, and this is what the image on your detector would look like. So one of the things that's always important to understand about imaging is what makes the spots, right? Why isn't the spot just point-like? How big is it? How blurry is it? And the thing that determines how blurry it is how good, well, it's always the same thing. If you look at the center of your detector, how good is the coherent addition of all these wavefronts? Well, the answer is it's perfect. The light from up here arrives at exactly the same time as the light from down here. Everything works out perfectly. The problem with diffraction, and the reason diffraction arises, is if you go a little off center, the cancellation, the peaks and the troughs adding up is not quite perfect, but it's not so bad either. So a little away from the center of a beam, you're able to get some of the energy arriving. You have to go quite far away, you have to go a couple of wavelengths away in a geometry like this to make the CCD actually show up dark. Because if you go up here and try to say, what's the timing it would take? How would these wavefronts arrive at the CCD up here? And you can calculate how they would arrive, and the way they arrive is with everything out of phase, and there's so many different phases that they all cancel. The fact that these spots are blurred out is fundamental to the fact that the waves are coming in as waves. And the fact that the focusing depends on the wave nature. The focusing is not geometric, the focusing is wave-like. So you really cannot focus any better than getting your wave addition over the whole aperture to be good in the center and not so good some distance away. So that diffraction spot is what prevented Sloan from seeing planets. It's what would prevent Keck from seeing a Jupiter's orbit planet around HRS 8799. So how do we get how would we get two stars like these two are kind of blurred together? How do we get them to resolve? It's even harder if you're not looking at two stars. Maybe you're looking at a star from this direction, and at a very small angle away, you're looking at a planet light coming in. So now you have a bright spot right next to a dim spot. The electromagnetism, it doesn't care. All these waves add up the same way, no matter how bright or how dim they are. But detectors don't. Detectors, maybe there's some noise in the detector. It could totally hide a dim object if it's close enough to a bright object. There's more noise close to this star than there is far away. So you need these diffraction spots to tighten up if you want to see the very tightly constrained things. One thing to tighten up is that you can the thing that determines the size of the diffraction spot is the wavelength. These waves would cancel out better if they were shorter wavelengths, or even if there were more of them. So now I'm going to zoom out and take the same image and the same angles. Here's Galileo's telescope. I forget what I was going to say about this. Same image, same angles, short wavelengths. You could say that either this is a shorter wavelength, or maybe it's the same wavelength as before, but with a bigger telescope. So now instead of drawing you a lens, which is 10 wavelengths across, I drew a lens which is 30 wavelengths across, something like that. And now the diffraction builds up more sharply. The center of the diffraction pattern is still really good at getting constructive addition of all this energy. But now you only need to go a tiny bit away, and the constructive interference is gone. So now that constructive interference has vanished between the star and the planet, and so you can get a nice little spot that receives just the planet light. It's not buried in the starlight. So bigger telescope makes this easier. And I want to point out, maybe this is all obvious. It's important to point out the better imaging of this planet is gonna benefit from the larger telescope in two totally unrelated ways. On one hand, a big aperture means better wave optics for getting the two spots to show up in different places. You know, one spot up here, one spot down here. That's entirely based on this distance measured in wavelengths. The other thing is having a bigger lens or a bigger collecting area means that there's actually more photons showing up in this little spot, which means it's easier to see. So collecting area and diffraction limit both benefit from making your telescopes larger, but they benefit separately. And that's going to be relevant later. Okay, so that's my little pitch for building bigger telescopes, just for getting spots like this separated. But the problem, and one of the reasons people were pessimistic about ground-based astronomy for a long time, is that that's the picture of what it looks like in space. Plane waves coming in from the star, hitting your telescope, and on the ground, as you all know, we don't have that. We have the atmosphere in the way. So what the atmosphere is doing is that there are little patches of atmosphere which are lower density than other patches. There are little bubbles, there are little eddies. A lower density blob of atmosphere. It's not just, so it's lower density, also different changes in humidity, but there are patches of the atmosphere which are delaying the wavefronts coming through more or less than other patches. So instead of having plane waves coming in, you have wobbly sort of distorted waves coming in. So this is what a ground-based telescope sees all the time. So obviously, the lens that you had previously designed to focus plane waves is not also going to focus these things. This is what the focus looks like in. So this is my little animation, but this is actual on-sky video from a group at I think they're at Harvey Mudd College that built a thing called RoboAO. So this is faster than your eye could see. This is sort of, I think, 100 frame per second detection of real wavefronts coming into what is this Palomar coming into this this instrument. And there are two things I should point out about it. One is, we talked about having a big lens means that your diffraction spot is small. That is still true after the atmosphere has gone by. If you can see this flickering star image, it has all this substructure. There are all these little tiny grains of pixelation inside it. The little sub-grains of this thing are the size that you expect from the whole diffraction pattern if your telescope was perfect. The fact that the atmosphere is in the way tells those, it means instead of having one little grain with all your energy, you have hundreds of them. And also it means that they change position and they change orientation hundreds of times a second. And that's what seeing looks like. That's what natural seeing looks like if you had a fast enough video camera and a bright enough star. So it's really ugly. So you can't, if one of these grains was a star and there was a little planet next to it, you wouldn't see that either. It's all just a mess. So the solution to that is this beautiful technology, which is now standard on all these big telescopes. It's standard, on one hand, it's standard. On the other hand, it remains highly controversial. There are lots of professional astronomers who kind of don't believe that it works, or who are pessimistic about whether it'll work as well as people say they do, or about whether it's worth investing in because we could do things from space instead. So it's as a physicist walking into astro departments, I looked at this thing, I said, oh, this is great, we've solved the problem. And then you talk to, I think this is also true at Case Astro. You talk to people, you say, oh, I'm going to go get this image I'm going to use the CAA. And they say, it's not going to work. That only works 2 nights a year. It's a terrible idea. But this is how it's supposed to work. So imagine you have a distorted wavefront coming in from a star that you think should have had planar wavefronts. One way you can do that is if you've got a bright star in the middle of your field. The other way you can do it is if you shoot a laser into the atmosphere and use the bounced back laser light. So the wavefront that's coming into the aperture of your telescope is all distorted. But if you bounce it off, if you send some of the light to a sensor, you can actually measure what the distortion is. If you know what the distortion is, you can invent on the fly a lens which focuses that particular distortion. I said, our normal lenses are designed to focus flat waves, but you can design a lens that'll focus anything you want. So if you know that, in this millisecond, the wavefront coming in looks like that, you can take a flexible mirror, reshape it on the fly with lots of little actuators to be just the right mirror to make that focus. Then you focus that. So I've got one more little video from you. This is from Ben Oppenheimer at AMNH. This is simulation. This is a simulated wavefront, but this is realistic atmospheric distortions. This is sort of what the wavefront looks like over the aperture of, I think this is a 2-meter telescope. I think this is Robo AO again. So it's just flickering all over the place. It's changing all the time. The waves are delayed by many wavelengths. It's not like, oh, this is a 20th of a wavelength correction. No, this can be a whole wavelength here and there. So this is what the wavefront looks like in real life. This is the mirror that you would invent on the fly in this control system to bounce the light off of. And this is what the wavefront looks like after bouncing off of this mirror. So if this was what was coming into your camera, this is what your image would look like. Natural seeing, blurred out, all these little speckles dancing around. You integrate for a few milliseconds and this would just look like a blur. This wavefront has one perfect speckle in the middle, which looks like the diffraction pattern in your telescope. It also has this fuzz around it, which has to do with the fact that this correction isn't perfect. There's all this high frequency noise here, which didn't go away. The mirror is never responding to the wavefront now. It's always responding to the wavefront a small bit of time ago. And so AO seeing can be great. It can give you a wonderful star image, but it's not, again, it's not perfect. You wouldn't have these speckles in space. But again, I love this video. It's very, I find it very informative. So yeah, so this is the technology. This is what one of those deformable mirrors looks like. It's a whole bunch of little piezoelectric pads on the back of a thin mirror, each one connected to a little cable that can make it jump up and down. The starlight, if you're not using natural starlight, you can use these lasers that'll send you back a narrow line of informative information from the upper atmosphere. This is my favorite AO image. Is this? This is the I think mostly Subaru telescopes aimed at the galactic center and watching a bunch of stars go around. This was a 20-year campaign of observations, and the first 10 years were done with natural seeing, and then there were another 10 years done with AO, and you can see it jump from one to the other. Natural seeing, big blurry stars, AO, diffraction limited stars. You can see you get better positions on what's there, and you can also pick up more stars. There's all these little things in the background that were too blurred out to see before the AO turned on. Okay, cool. So yeah, so this is going to be standard instrumentation on all your big telescopes. GMT, ELT, TMT, they all have at least specs written for what this AO will look like. Is that good enough to see exoplanets? Maybe. And I said that there's controversy among astronomers about how well you expect this to work. So this is one of the National Academy of Sciences sort of exoplanet guidance documents. They made this plot, which is the two things you care about for finding an exoplanet. To get an image of an exoplanet, it needs to be brighter. It's not going to be as bright as the star, but it needs to be some decent fraction of the star's light needs to bounce off the planet. Is that fraction a part in 10 to the 4, 10 to the 5, 10 to the 6? Then that's a good bright planet. But 10 to the 8, 10 to the 9, those are really dim planets next to big stars, so they're harder to see down here. You also need the star to be far enough from the planet that your telescope can separate it. So the best people have done with 8-meter telescopes is up here. You could see, we think we would have seen planets if they're an arc second away from the star and 1 part per million of the brightness of the star. The 30-meter telescopes, if you're an optimist, oh yeah, and then the 3 different, so I've got Jupiter-y type things, Neptune-y things, they're dimmer, and Earth things are really dim. Their rocky planets are so small. So if you're a pessimist, you think that these 30-meter telescopes are going to bottom out up here, AO a little better than we can do today, but not much. And if that's true, we'll see a couple of Jupiters. We'll see some HR 8799 things with Jupiters around them. Okay, that'd be disappointing to me because I want to see Earths. The optimists think that we'll see lots and lots of Jupiters because by 2040, we'll have invented AO. It's a factor 100 better. And if you're that good, and if you can work really close to the diffraction limit, you will see Earths, or at least we expect to. But yeah, but nobody can agree on where this line is. You're always better going closer, and you're better going brighter, but how do you do that? But a few Earths in there, that's good. Space telescopes go straight down to really dim things, but they can't get really close because they're never going to have a 10-meter aperture. They're always going to be, space telescopes are hard to build even at the 2-meter scale. So on the ground, these 30-meter telescopes cost $1 billion. And I think we have a pretty good understanding of why. Prior to, if you had proposed 20 years ago saying, oh, I'm going to go out and build a 30-meter telescope, and you ask people what'll it cost, they would show you this plot. This plot is just a catalog of telescopes that have been built and what they have cost. That includes amateur telescopes that people have built at home or you can buy off the shelf. They cost, these are $1995. The bigger ones cost a few tens of thousands of dollars. The in-between ones, these are sort of the Mount Wilson Palomar scale, the meter-ish scale telescopes get more and more expensive as you get bigger. And there's just a totally predictable line through here. This spans 80 years of telescope construction. People figured out how to make them bigger, but making them bigger makes them more expensive. And then once the sort of lightweight mirrors and segmented mirrors made everything get cheaper by a factor of several. They didn't, Keck is not on this line, it's below this line. But it still seems that making bigger versions of Keck is going to get more expensive. And the scaling law is kind of like this, diameter to the 2.7 or diameter to the 2.5. That is actually pretty good at predicting the $2 billion budget of TMT. So TMT is up here at a 30-meter telescope. If you follow this line up, it crosses $1 billion and gets to about $2 billion. So they want to have invented a cheaper way of doing it, but they didn't. They just took the old way of doing it and did it bigger with comparable costs. That's not, notice this is a log scale. So, saving a centimeter on your screen is saving enormous amount of taxpayer money. So this is worth doing. So I spent a while looking into this. None of this data is public. Nobody publishes papers on the construction budget of giant telescopes. I had to send an undergraduate to the Caltech archives to get stuff out of paper file cabinets for me to understand what some of these costs came from. At the 10-meter scale, you spend about the same on the mount, the dome, or generally the mountaintop infrastructure, and the mirrors themselves. In segmented telescopes, the mirrors, basically you're paying for area. You want 10 times the area, you pay 10 times the mirror budget. Cost proportional to area, is proportional to diameter squared. The problem, the scaling law is steep because of everything else. If you have a 10-meter mirror, you need to have a 10-meter tilting structure that'll point it at the sky in any direction you want to. You'll need to have a 10-meter spider that reaches up above it and holds the secondary. So all of the difficulties of building these things get harder as the cube of the area. If you wanted a 20-meter, it gets 20 meters harder in this direction and 20 meters harder in this direction and 20 meters harder in height. And so it scales as worse than d cubed. Similar is true for the dome and the infrastructure. The giant foundations that hold these things up are expensive. So I spent a while working on, and this was a sort of a side project of mine for the past couple of years. Is there a way, I'm not, as a particle physicist, I cannot invent a cheaper way of building mirrors. There are people who work on that, but I'm not one of them. But I've done lots of mechanical engineering of large objects, so I was wondering about a cheaper way of doing the rest of this. And so in the context of a different experiment where I had to design a really tiny weird optics table that squeezed into a really small space, I had a geometry that reminded me of this. This is a radio telescope called a Krauss-type radio telescope. This one was at Ohio State. It's not there anymore. It was called the Big Ear. And this did something really weird with all of its radio telescope collecting area. It had a giant flat structure, which could tilt. And all it could do was tilt. It had no other degrees of freedom. So this thing would tilt. It could tilt horizontally or it could tilt vertically. No, go back. And all that did was take light from the sky and aim it so it was horizontal. Once that light was horizontal, they intercepted it with this big parabola, and that parabola sent the light back to the ground. So this is a geometry where you can get lots and lots of area, but you do not have to lift it high in the sky. So I mean, this thing is a 100-meter radio telescope without 100 meters of bearings and gears and things that lift it up. It's not the Green Bank telescope. It's a much more compact thing. There's another one of these. This one is still operating in France, the giant radio telescope of Nancy. So being radio telescopes, the way these work is they would collect light from a given zenith angle. They would tilt this thing. It would pick a point of the sky. And then their camera, their little radio detector would move to track the focus they could track for sort of an hour while the sky spins past this instrument. But they couldn't really steer. It's not a fully steerable telescope. But I realized you could do this in the optical. This is radio, but you could do exactly the same thing in the optical. And it's not that hard to make it steerable. So here's my top view of a big ear style telescope in the optical. So imagine starlight is coming into your screen and hitting this big diagonal flat, the siderostat. Whatever angle it's coming into your screen, you can set the siderostat to make that go horizontally and make it bounce over to this parabolic primary. So if the star were just passing straight overhead, if you were at the equator and if this was north-south, the star would always be focused here. But what if the star is not passing straight overhead? What if it passes a little to the north? If the star passes a little to the north, then once this beam has been folded, it'll be heading a bit southwards. The primary doesn't have to lift up to intersect it. The primary just has to slide over to intercept it. This is something I've explained this many times in person to people, and I have kind of an interpretive dance to do to show you, but you'll have to do it based on the screen. So the primary is on railroad tracks and can slide back and forth along the ground, doesn't have to tilt up. The siderostat only tilts, it only rolls, doesn't have to tilt up. So now we've had the big ear thing, we can build a radio telescope, an optical telescope that's huge and has lots of area, but doesn't have a bunch of infrastructure to lift it up. Here's a side view, just in case that optical path was not clear. It's probably not. I've taken the side view, I've cut it in half, so these things are actually really far apart, but starlight comes from above. The siderostat, which can tilt different directions, tilts in such a way that you fold this light horizontally. This is your only major focusing element. If you wanted this to be a Newtonian, you would just put your camera over here. This picture happens to be of a Rishi-Crescien, which means there's an extra fold. And you can actually have your instrument rooms stationary. You don't need the camera to move with the telescope. The cameras can just sit there, which is kind of nice. In terms of infrastructure, the way I would build this is, so this is a zoomed in picture. I'll zoom out in a second. This is what a 100-meter telescope would look like. Nobody else wants to design a 100-meter telescope anymore, but this is a 100-meter telescope made out of 50 of these 2x2 meter squares. Each one is on a little pedestal. That's just kind of simple steel infrastructure, very cheap. The squares cost $2 million each in terms of, so that's what it costs to polish 4 square meters of mirror. But everything else is just cheap. You could build it in you could hire a local welder to slap this together for you. So I'm going to zoom out, you'll see what the whole thing looks like. This is a person for scale. Here's this enormous wall of parabolic mirror. Here's the tilting structure that gives you the siderostat. The other thing I think this telescope needs is that this beam, once this beam goes horizontal, it spends a lot of time going back and forth near the ground. That air is pretty warm and pretty turbulent. I have an undergrad working on this summer, but I think that putting a baffle around that horizontal beam would destroy most of the turbulence that would make the seeing worse. And I think this would actually be a decent telescope in terms of the optical quality before AO, which means I think the AO would probably work. That's a difficult question though. So again, starlight comes into the siderostat, goes horizontally to the primary, wherever the primary is, and then comes back to focus. 100-meter telescope. So I'll show you the budget for this in a minute. So I tried to budget these out at a couple of different scales. This is sort of the university scale. I would like to convince Case Western to build one of these someday. But there's not quite, it'd be fun, but there's not really a science case for it. So it's a 10-meter long, kind of 30-centimeter wide iteration of the thing. One of the nice things about it is it's trailerable. You could build this here on campus, slide both pieces into a shipping carton, truck them to kit, you can put them back down again. This one, the 100-meter one I showed you before, I call WHAIT, the hectometer wide aperture exoplanet telescope. So that is 200 square meters of collecting area. So it's like 2.5 keks, but it's 100 meters wide. So it has 10 times the resolution of Keck. for if the target is lined up on the sky, right? Oh, and then here's my budget. This is one of the least certain numbers I've ever put in a publication in my life, but I think it costs about $150 million, which is an eighth of what they're spending on TMT at the time I was writing this slide, which was years ago, a tenth of what they thought they were going to spend on OWL before they decided OWL was crazy. So I drew this first at 100 meters, but I said, is there anything stopping us from going bigger? I mean, we have more than $150 million to spend on telescopes. How big can we go? So I went ahead and sketched out, in AutoCAD, I went ahead and drew the 300 meter version. So that's 20 times the collecting area of Keck, 10 times the resolution of TMT. It's basically, to cost it out, one way to cost it out is to say that if you just bought all of the Keck glass, you buy 20 copies of Keck, put them on really simple mounts, and just line them up in a circle. That came to under $1 billion, which is pretty good. If you had some of the modern mirror innovations, it could be well less than that. And this is an economy of scale, which might make that worthwhile. So I'm really excited about this design, but it's just so far out of current experience that nobody really knows how to evaluate these. So I went ahead and put this on exoplanet discovery, which is kind of what I care about. So here's the same plot I showed before. Here's all kinds of different planets that are in a synthetic survey. Things that are too close to the star are over here. Things that are far away are over here. Bright things, dim things. An 8-meter telescope can see none of this. It's just too small. A 30-meter telescope, and this is an optimistic 30-meter telescope, can see some of it, but mostly only the gas giants, these little pluses. That's what you get for $1 billion in a round aperture. And this is what I think, and I said there's a lot of uncertainty here, but if the AO works here, and if there's not something horribly wrong with this AO, here's your $150 million telescope. 100-meter aperture means that it can get really, really fine resolution. It can get really close to the star, so it can get down here to really, really closely separated planets and stars. They're only a little dimmer than, some of these are quite bright because they're sort of Mercury-like objects in really close orbits. And you get a bunch of them. You get Earths, you get Jupiters, you get Neptunes, you get everything. If you go to 300 meters, you get everything, not just the lucky planets that happen to be perfectly situated for observations, but you kind of get the whole population of possible planets if you believe this plot. Should you believe this plot? I have no idea. This is something I'm working very hard on. I have undergrads helping me this summer a little bit. I'm trying to interest the astro community in doing more simulations. Nobody really knows for sure what contrast limits would look like for this aperture, for this scale. Our seeing is going to be somewhat worse because we're so low to the ground. How much worse is that? Nobody knows. So if you move these lines up and down a bit and say, oh, it gets worse, I still think it looks like a good telescope, even for the sake of seeing the bright things that are so close in. So I'm excited about this, and I'm continuing to study and publish it. Let me wrap up there. Actually, I have to go put kids to bed pretty soon. My summary is that exoplanets, I think, are interesting. I have what I hope is a new direction for someday building the telescopes that'll see them from the ground. And then for this audience, I want to add that I'm working on this kind of by myself and with occasional help from students and undergraduates. If there's anybody out there who's retired engineer who wants to contribute some expertise to doing some of this design work, I am happy to crowdsource a bunch of stuff and try to bring in collaborators. There's a job for pretty much anybody who cared to show up and do something. And you can email me later if you're interested in doing that. Cool, that's my talk. I'll be happy to, I will stop this share. I'll fire up the chat window and I'll take any questions. Or, if it's easier to unmute yourself, go ahead and unmute yourself.
To unmute yourself, just press spacebar, one person at a time, please. So press spacebar and hold. There you go. Robert?
Yeah, okay. Bob Fritz here. It seems to me that your resolution, your new concept is 300 meters wide, but only a couple meters tall. Yeah. And I would think the resolution would be much greater in one direction than the orthogonal direction. Is that correct?
Yeah, that's right. So when you're looking at, especially for exoplanets, they're going around the star. So most of them will spend at least some time on the side that you're good at seeing. But then if they go to the other side of the star, your diffraction pattern gets bigger and you wouldn't see them then. You lose about a third of your targets by having this limited directional resolution.
Okay, and this seems, follow-up question, this seems like such a obvious idea. I'm surprised nobody thought of it 25 years ago.
Yeah, I ask myself that all the time, and maybe it means there's a showstopper, but I haven't found one yet. Oh, I should say, one of the things that a lot of this has not been done long ago is, prior to adaptive optics, there was no point to building telescopes this big. It was just a total waste of effort, because as soon as you actually, as soon as you get the area that you want, in a telescope that's bigger than a meter or so, all of your additional diameter contributes to making the speckles smaller, but you can't see the speckles anyway. You're just seeing the natural seeing. So nobody prior to, say, year 2000 would have cared a whit about designing a telescope that got more than a couple of times better seeing than natural atmospheric. Yeah, there is that. Oh, and I should say, there's also, there's astronomers telling me that this is a terrible idea today, and so maybe it is a terrible idea.
I want to thank you too for giving the talk, Ben. How much of the adaptive optics that they're talking about now have as its genesis the problems that they had, that they experienced with the Hubble and the corrections that they sent up? Is there some kind of a route there that they said, well, now that this works, we could do this?
No, I think the adaptive optics has its root in even at the 8-meter scale telescopes. Before they had adaptive optics, they had what's called active optics, which is when you take an 8-meter mirror and you tilt it, it sags a bit. You can't keep the figure exactly rigid at all angles. So these telescopes have had, even since the 1990s, an active sensing loop that would take an image of the sky, calculate how the mirror was distorted, and refocus it. And they could do that in real time. Because that only has to follow the tilt, it only corrected it every couple of seconds. So I think it's the people realizing that you could do that faster if you have bright enough sources that the AO comes from. In space, it's totally irrelevant because there's no atmosphere. You don't need adaptive optics in space.
Okay. Well, I think, Tim, why don't you finish up here and thank our speaker, and then turn it over to Bill.
Okay. Once again, Ben, thank you very, very much for coming, and
Okay.
Sure,
very
thanks.
interesting talk, and thanks for doing it via Zoom. I initially was kind of reluctant to ask my speakers to do it this way, but it seems to be both necessary and really quite workable.
Yep. Mm-hmm.
Again, we're in the comfort of our own homes with our own cocktails and no pants. So thank you very much.
Thank you for having me.
Let's go to Mr. President.
I'll head off and put kids to bed, and I'll leave you all alone. Bye-bye.
Thanks, Ben. Thank you very much.
Bye-bye. Thank you. Nice.
All right, Mr. President, you want to unmute? Bill? Hello, Bill?
I'll get him.
Okay.
Okay.
Oh,
Gotcha.
yeah,
I
he's
think
good.
I'm unmuted now. Can you hear me?
Yeah.
Okay, and our thanks to Professor Monreal for a very interesting talk. And our very first ever Zoom meeting. I want to thank Jay and Tim for setting this up. And I guess I should look at the camera when I'm talking. We ordinarily, of course, would have a break with donuts and coffee. And I am missing the donuts, of course. I always look forward to my monthly jelly donut at our meetings. But we can proceed with our meeting. We'll have a brief business meeting, and we'll start off with our treasurer's report. Ron Palcic. Is Ron here?
Yeah,
Yeah.
I just had to unmute. Let's see, for May in the bank, we have $8,252.82. Petty cash, $408.65, for a total of $8,661.47.
Thank you, Ron. Any questions on the treasurer's report? Okay, hearing none, the treasurer's report will stand as published in the Observer. I'll call on Trevor for our secretary's report, even though there isn't any because we didn't have a meeting last month. But Trevor, anything you would like to say? Is Trevor here?
Yeah, Trevor's here. He
needs
is
to be unmuted.
unmuted. Stand by a second. Okay, Trevor, go ahead.
You all hear me now?
Yeah, we
Can
can
you hear me
you.
now?
Yeah.
Okay, yeah, I don't have anything to add. Very important message there. So I'll have a riveting secretary's report for next month.
Awesome.
Sounds good, Trevor. Thank you. Okay, we'll go into a president's report, a brief one. As you know, that unfortunately, because of the coronavirus, our live club meetings have been canceled by the Rocky River Nature Center and by the Metro Parks, out of a safety precaution. We, as I mentioned earlier, were canceled through the August meeting. No word yet on the rest of the year, although there's a possibility that those meetings may be canceled also. And we present the programs on behalf of the Metro Parks, and where we meet in their facility, so they control whether or not we can have our meetings here at the Rocky River Nature Center. The public star parties for the Medina County Park District, as I mentioned in the Observer, if you've read that, they also have been canceled through the August meeting, or through the August star party. So we have two star parties left after August, September, and October. So far, they are still scheduled. And they're both, I picked starting times at 8 p.m. And at least one of them is going to be a totally dark sky event, no moon at all. And that should be, hopefully, if we have good weather, which, the weather's been great lately. And so here we are, we can't meet, we can't have our star parties. And so it's just totally unfortunate what's going on with this. We possibly may have a library program, a moon program for the Beechwood Public Library on September 22nd. That's up in the area also, depending on the library system and what they decide. In lieu of public events, it would be nice if we could schedule some private star parties for club members out at Letha House, either by the parking lot there, or else over in the field by the pavilion, if we have good weather. And these would be ad hoc, and what it would take would be somebody to say, hey, let's have a star party. We're going out tonight to Letha House. I don't recommend going out by yourself. It's always better to be in a group, especially since Letha House and the Metro Parks are relatively isolated. If you choose to go out to the Metro Parks, please remember to follow the rules that are listed in the Observer, and cooperate with the Metro Parks Police. And so far, they've been very welcoming to us, and as have the Medina County Sheriff and the Medina County Park District. It was nice of the director of the Medina County Park District to approve us going out to Letha House for individual observing. He said it's fine, it's up to us, and he's on board with us with it. The only other thing I would have is to call for observations. If there are any observations, please speak now. Forever hold your peace. We've had a lot of clear skies, and it would be, people have seen the International Space Station with the Dragon capsule. I've seen that. we've gotten some nice moon shots and some good pictures. And I think Matt, was it Matt Franduto who got a shot of Comet Swan, or maybe it was John Birkin, I'm not sure.
It was Matt.
Was Matt, okay, yeah, Matt as always comes up with something, as does Dave Watkins, who does a great job also, and Alan Stute. And Alan had a very nice series of moon shots. The moon is one of my favorite topics. And personally, I've been disappointed this summer because I bought a brand new zoom lens, the zoom eyepiece for my telescope, and was looking forward to trying it out at Letha House on one of those nights where the sky is full of stars. And so far, no luck. Viewing here in Strongsville is not the greatest. I can see the moon, I can see some of the brighter stars, but that's about it. But are there any questions about the club, the operation, or the Zoom meetings?
Quick correction, Bill. It was John who got the Swan, and it was Matt who got the space station and the following the Dragon for the
Okay.
pictures. Yeah.
Got them mixed up, sorry.
I did.
Oh, you did, okay,
I did. Yeah.
yeah, okay. Any other questions?
I just figured out how to unmute.
All right.
So I saw the whole presentation. It was great.
I have a question. Can you hear that?
Yep.
Sure.
Yep.
Go ahead, Steve.
How do you get, I've got my name and not my picture. How did you do that? Am I doing something wrong or didn't see something?
Yeah, there is a command down at the bottom, I believe, where you can join with video. I believe when you first come into
I probably
Zoom.
screwed that up.
Yeah,
Yes,
it says start video.
Oh,
Yeah. And if you hit that, you should be able to appear.
You will appear magically,
It's magic.
and then you will
says
unmute.
Zoom is,
Oh, you've already unmuted. So.
says Zoom is unable to detect the camera. Maybe I don't have one. I don't know.
Maybe you don't.
Yeah, down in the left-hand corner, there's a picture of a camera.
Yeah, Tim, he may
And
not
if
have a
you-
camera.
That's
the
okay.
problem.
That would complicate things.
How many people, Jay, did we have tonight? Did you have a count?
Yeah, we had a total of 27 participants tonight. Yeah, total.
That's good. I mean, for a first effort, I think that's pretty good. That's about a little less than half of what we would have at our live meetings, where we generally get 60 to 65 people. And I think maybe as time goes by and we're forced to do more of these Zoom meetings, that more and more people will join in, hopefully. And it's a substitute for the live meetings, which I think are preferable. But this is a good way to still have meetings and deal with the coronavirus situation.
I have a question.
Something I forgot to mention. We possibly may have a club picnic.
What are you doing? I have.
Hold on. Please we can only speak one at a time. Please let Bill finish and then ask your question. Continue, Bill.
Thank you. Had a weekend in August, either a Saturday or Sunday. Rich and Nancy Whistler are willing to offer their home again and their backyard, their very spacious backyard for the picnic. And Dave Nudie and friends are willing to help put it on. So we'll see. Stay tuned on that. Like I mentioned in the Observer, please, we hope that you can participate. Any other questions?
If you have a question, please press your space bar to ask your question. Please continue.
Do you want me to talk about upcoming meetings?
Yeah, Vice President's report. Sorry,
Oh, that's all right. That's okay. Yeah, tonight obviously was Zoom. We will continue to do this via Zoom at least through August. And I have speakers through August. September is up in the air, and we'll see. I've got a couple of people we'll be talking to, but definitely we're good through August. Next month, we have Steve Spears. He will be talking about a mathematical investigation of the properties of Wolf-Rayet stars for the amateur astronomer. This is a field that he's very interested in and has been doing quite a lot of work in. Basically using inexpensive equipment, elementary math, and some various laws, you can determine the mass of stellar and black hole binary systems. Any event, that will be next month. August, we have Gary Cater, club member and director of the Burrell Observatory at Baldwin Wallace. He will be talking about the Hertzsprung-Russell diagram, which is the Rosetta Stone of stellar astronomy. And that diagram is most important tool for understanding stellar astronomy, not only how stars are born and how they live and die, but also estimating distances and dating star clusters. Alan and Gail do want to do their presentation, but they want to do it live. So I took them out of the rotation, and I will stick them in as soon as we come back to doing live performances. And we've got a couple of other people. So that's pretty much all I've got. I do have an observation section for the newsletter. So any contributions are always welcome. But of course, if we're doing live meetings or Zoom meetings, do the observations here as well. That's all I've got.
I have a question.
For me or for the world?
For Tim. For Tim.
Okay.
Yeah. Is that a dead raccoon in the back behind you there? Because everyone's wondering what the heck that is.
Yeah, that's tomorrow's dinner. We got that. I found that this afternoon out front. Truck, I guess, got it, and we're. I'm looking up recipes now online. If anybody knows how to cook, I don't even know what the heck it is because it was crushed a lot. But I'm hoping it'll be tasty with a nice potato salad and a Chianti. That's Buddy. That's our cat, our male cat. He is the master of napping. I've learned quite a lot from him about napping. And he watched the presentation, but now that I'm talking, he said, yeah, I'm going back to sleep. But that's Buddy.
Okay.
And he's alive, by the way, we think. Hasn't moved in a week or two, but you know.
Okay.
Okay, thanks, Tim. Any other comments from anyone? Well, I'd like to thank everybody who joined us this evening for our first Zoom meeting. And again, thanks to Jay and to Tim. I think it went well compared to some I've seen. And the speaker came across very well, and it was a good talk. And if he's still listening, I'd like to thank Professor Monreal for his presentation.
He's gone.
And
he went to put the kids to bed.
And it's good to see Ted. I haven't seen him in a long time. And I always like to see Nora. Hi, Nora. And and everyone else, Paul and the dog there, Kai, I don't know whose dog that is. And hi, Jim Guilford and Trevor and everyone else. Thank you very much for joining us. With that note, I would, Shay, you have a question? No, okay. With that note, I would adjourn our meeting. Thank you for coming. Yes. Yes, Paul.
The weather was looking pretty promising next week, and man, I'd love to get out to Letha if anybody else is interested. I'm retired now, so most any night works for me.
I'm good Wednesdays. Wednesdays are good for me.
Okay.
So if it's clear, I wouldn't mind going out there.
Okay.
Yeah.
If I can find my telescope, it's been a while.
I'm good. I'm also retired, of course, and I'm good just about any night. Except this week, I have a meeting I have to attend to on Wednesday. But other than that, I'll be good too.
All righty.
Okay, I guess that should do it. Thank you very much, everyone, and we'll see you next time.
Thanks a lot, guys.
Thank you, Jay.
Good night, everybody.
Thanks,
Thanks,
Jay.
Jay.
Good night, all.
Thanks, guys. Live long and prosper, John.
Yeah, yeah.
Great seeing you all.
So how's the skies?
Hi, John S.
Okay. All right, if we're all done, I'm gonna close her up here. So, okay. Jim, thanks for your help. I'll convert this and upload this within the next hour or so. I'll send you an email, okay?
Very good. We'll have it up.
Okay, thank you. All right, good night, everyone.
Yeah, see you, Bill.
Bye.